Hi friends, today our topic is how robust are gossip-based communication protocols. Firstly, I would like to tell some definitions regarding this. Gossip-based communication protocol. A gossip protocol is a procedure or process of computer-to-computer communication that is based on the way of social networks disseminate information or how epidemics spread. Robustness. The quality or condition of being strong and in good condition is called robustness. Incentives. A thing that motivates or encourages one to do something is called incentives. Abstract of gossip based communication protocol. These are often touted as being robust. Nothing surprisingly, such a claim relies on assumptions under which gossip protocols are supposed to operate. We will discuss some cases, expose some of these assumptions, and discuss how sensitive the robustness of gossip is to these assumptions. This analysis gives rise to a collection of new research challenges. A brief history regarding gossip based communication. There are three types of approaches to forward or mixing the multimedia streams. Firstly, centralized approach. Here, a server is present where every peer is connected to the server and every information is passed from the server, which uses a centralized server for forwarding and mixing of multimedia streams. And the second one is fully connected overlay approach, where all peers are in direct contact with one another and there is no server involved in this. The third one, which is our main topic, gossip based approach. Here, peers operate in parallel and randomly, and each peer communicates with one or more randomly selected partner. Introduction to gossip-based communication protocol. This is an attractive technique to manage inconsistencies that arise in distributed systems. They are simple to implement and highly resilient to failures. Messages can be broadcast with high reliability. Messages are steady throughput despite high network packet loss rates and high process failures probabilities. Work on database replication and multicast, many have considered gossip protocols and touted their robustness. The robustness claim is often backed up by analysis, accounting for message loss, process failures too, topology changes, and so on. They also rely on a set of additional assumptions about the environment in which the protocol operates. Somewhat disturbingly, that gossip's ability to deliver on its promise of robustness depends crucially on a handful of assumptions that are often left unspoken and as such have so far largely escaped those scrutiny. It is an exciting open research challenge. Background of gossip based communication protocol. Each process periodically and randomly selects a partner with whom it exchanges recently observed information. In their periodic work, a gossip-based protocol is used to resolve inconsistencies among clearinghouse database servers. In each communication round, a database replica randomly selects other replicas with whom it gossips about recent database updates. Gossip protocols can be adapted to tolerate a certain number of process crashes by adjusting the maximum hop count and fan out parameters. Most gossips assume crash failures. Later, works on Byzantine gossip protocols differ from these first efforts by relying on cryptographic primitives. Johansson et al. Designed Fireflies, a Byzantine fault-tolerant membership management protocol that allows processes to maintain a reasonably current view of a system's member. Here are few examples for gossip-based communication program. To, to, to start the search, a user would ask the local agent to begin to gossip about search string. That is, we assume a random user is searching for a search string where it should find its partner and then he can connect to them. Agents also gossip about the best match today. Thus, if A gossips with B after the interaction, A will know of the best matches known to B, and vice versa. Best matches will spread through the network, and if at all another user accesses the A or B, they can get all the best matches involved in this transaction. Much like real life rumors uh, or gossips and virus spreading like corona, etc., information disseminated by gossip protocols spreads quickly and reliably with high probability. Here is a pictorial representation of gossip-based communication protocol. It itself keeps a boundary where it should where it should not exceed that one. Here, these buildings are represented to be a server, and they access randomly and parallelly to the other servers where the best matches from A is being sent to B and so on. Here comes the gossip protocol types. There are two types of gossip protocol: dissemination protocol. These use gossip to spread information. They basically follow by flooding agents in network, but in manner that produces bounded worst case loads. These are also called rumor mongering protocols. These use gossip to carry out multicast. They report events, but the gossip occurs periodically and events don't actually trigger the gossip. One concern here is the potentiality high latency from what the event occurs until it is delivered. Background data dissemination protocols continuously gossips about information associated with the participating nodes. Typically, propagation latency isn't a concern, perhaps because the information in question changes slowly or there is no significant penalty for acting upon slightly stale data. The second one is protocols that compute aggregates. Aggregates is a group of cells. These compute a network-wide aggregate by sampling information at the nodes in the network and combining the values to arrive at a system-wide value. The largest value for some measurement nodes are making smallest, etc. The key requirement is that the aggregate must be computed by fixed size pairwise information exchanges. These information typically terminate after a number of rounds of information exchange logarithm in the system size, by which time and all-to-all information flow pattern will be have been established.
Here are some hidden assumptions in gossip protocols. Any protocol makes certain assumptions about the environment in which it is deployed in order to guarantee certain properties. These include assumptions about network latency and bandwidth, processing time, failures, and so on. If such assumptions are made explicit, then the burden lies on the deployer to make sure that the assumptions are satisfied. However, in this section, we present a set of 5 commonly made assumptions that are typically not made explicit. Yet, gossip protocols rely on these assumptions just as much as they rely on explicit ones. The following slides will contain the 5 assumptions in gossip protocols. Here are the 5 assumptions in gossip protocols. These 5 assumptions will mainly concentrate on the following factors. The first one mainly concentrates on participants that gossip with one or more partners at fixed time intervals. And the second one is there is a bound on how many updates are concurrently propagated. And the third one is every gossip interaction is independent of concurrent gossiping between other processes. And the fourth one goes like any two processes can discover each other independently of the gossip mechanism. And the fifth one is processes select gossip partners within a round in an unpredictable, random like fashion. Here comes the first assumption. This assumption is technically a synchrony assumption. That is, the clocks at the different processes have the same rate of progress and the processes gossip in real time and are not arbitrarily slow. If, for example, gossip intervals were made very short compared to network latencies and CPU processing times, then most published analysis of gossip would certainly not apply. On the other hand, increasing this delay impacts the latency of gossip dissemination. A synchrony assumption can even purposely be invalidated by a malicious denial of service attack either at the network level by increasing network latencies or at the application level by creating large amounts of information to be gossiped. This is the second assumption, and this assumption relates to the amount of resources that processes need to provide and may impact gossip's scalability. Most gossip protocols assume that processes have sufficient resources available and that gossip never exceeds these limits. Hence, they typically do not consider what happens to a gossip protocol whose demands grow to require more resources than many of the participants are willing to budget for. Even if we assume there are sufficiently many resources available for storing information, it is hard to ignore gossip's communication costs. Although it can be unacceptable for many applications, such behavior can easily occur if some processes slightly diverge from their expected execution steps. Here comes the third assumption, and this assumption states that in reality, gossip messages are transferred over the underlying physical communication graph. As a result, various communication failures are often correlated, but most analysis of gossip assume that message loss failures are independently distributed. Even in the absence of link failures, loss is often caused by queue overflows at routers, and indeed, random gossiping between end hosts could result in a highly uneven load on routers in the physical network. Finally, there is often a considerable amount of heterogeneity in real distributed systems. Not all processes are the same, not all links are the same, and not all routers are the same. And here is the fourth assumption. It is clear that any gossip protocol needs some kind of bootstrap mechanism whereby newly joining processes can discover one another. However, it is perhaps not obvious that this mechanism has to be available continuously. It is therefore necessary that these processes may refer back to a discovery service in order to rediscover each other. At the same time, for efficiency, it is important that the processes cease trying to gossip with the partners they can no longer reach. But herein lies a problem as well. If they do so and the network partition heals subsequently, gossip by itself may fail to rejoin the disconnected processes. Again, the system relies on a discovery service to reconnect the processes. And here is the final fifth assumption. This assumption mainly explains like random partner selection seems to be an essential aspect of gossip protocols. If the selection is not random, then an application could be adversely affected. In some environments, using a suitable pseudo-random generator is sufficient for partner selection. In settings in which processes behave selfishly, however, there may be incentive for a process to not use such a generator. Consider a selfish process S interested in the data from process T. Nothing prevents S from initiating gossip with T each round to get early access to T's data, and subsequently S may be uninterested in gossiping with other neighbors. By examining the above all assumptions, here are some points to be discussed. We do not claim that the above list of assumptions is comprehensive. There are often other hidden but obvious assumptions in any protocol. For example, if processes choose partners uniformly at random, memory overheads on processes would grow linearly in number of processes. While this overhead matters little on current desktop machines, the memory on nodes is a sensor network could be severely limited. The point is that for every gossip deployment, we need to revisit our assumptions and justify them in the appropriate light. There are also many challenges for the above discussed five assumptions, which questions the gossip's robustness properties, and these challenges are explained in the further slides. They have proposed research challenges in maintaining and in some cases restoring gossip's robustness properties for all the following hidden assumptions. Here is the first assumption and the challenge for the first assumption. From the above assumption, many gossip protocols rely on synchrony assumptions. A natural evolution of research in distributed systems is to understand possibilities and impossibilities if we move to a weaker system model. For instance, in the context of consensus, it is impossible to guarantee termination, even for a single crash failure. This could also be natural direction for gossip protocol towards a better understanding of the guarantees we can hope for when changing the system model. What are the failures we could cope with if we apply gossip in an asynchronous model relying on fair links? Is it still possible to guarantee that dissemination of updates reach every correct process with probability 1? Here is the second assumption and the challenge that it faces. Revisiting the Revisiting this assumption, which highlights a difficulty of resource constrained approaches in the context of event dissemination, of fairly small increase in the message rate can be sufficiently be overload buffers and even worse, overload the entire event dissemination system such that latencies grow without bounds. Could we use resource management to establish alternative ways to address consistency for applications? Can we ensure that the resources are managed decentralized in a fair manner, and what happens if we need to manage resources when processes behave selfishly or otherwise mysteriously? Here is the third assumption and the challenge it faces. The third assumption is every gossip interaction is independent of concurrent gossiping between other processes. And the challenge this assumption faced is in this assumption, we find that in many cases the selection of gossip partners show dependencies with respect to the underlying communication graph. That is, failures could be correlated and communication delays may be unevenly distributed. However, it is still possible to set up logical but partially connected communication meshes on which it is possible to gossip successfully. How should these meshes be designed so that interaction between the logic links are minimized? Here is the fourth assumption and the challenge. Any two processes can discover each other independently of the gossip mechanism. Looking at the assumption, we can see that discovery is an important part of a deployed gossip mechanism. Still, there does not exist much research devoted towards this issue. It would appear that a system addressing discovery should be aware of the physical topology of the network and sufficiently decentralized in order to make sure that every node can access the discovery service at any time. While such a service may use gossip internally, it would seem that there is a chicken and egg problem. Here comes the final assumption and the challenge that are faced. The final assumption is like processes select gossip partners within a round in an unpredictable random like fashion. And the challenge is many have taken gossip as a scalable and robust way to disseminate information in a peer-to-peer environment. Yet at internet scale in which each machine corresponds to a user and many users are selfish, we need ways to enforce our partner select algorithms. A limitation of Lee et al. Approach is that the checking step relies on all processes sharing the same static global membership list. Is it possible to combine elements from Lee et al.'s approach with the large body of literature on maintaining partial membership lists? The following are the conclusions that can be drawn by reviewing the overall presentation. Like many other protocols, gossip protocol rely on a set of assumptions. Exposing these assumptions is crucial to understanding the robustness of the protocols that rely on them. We reviewed several assumptions made by gossip protocols and explored the impact of invalidating the assumptions. This in turn suggested various research directions. And this is the explanation of how robust are gossip based protocol. Thank you.